Black hole morsels? In the realm of theoretical physics, few concepts have captured the imagination as profoundly as black holes, regions of spacetime where gravity is so intense that nothing, not even light, can escape. In 1974, Stephen Hawking revolutionized our understanding of these cosmic enigmas by proposing that black holes are not entirely black. Instead, they emit a faint glow of radiation, now known as Hawking radiation, due to quantum effects near their event horizon. This groundbreaking theory bridged Einstein's general relativity with quantum mechanics, offering a tantalizing glimpse into the quantum nature of gravity. However, detecting Hawking radiation from massive astrophysical black holes has remained elusive due to its extreme faintness. A recent study published in Nuclear Physics introduces a novel hypothesis. During violent black hole mergers, tiny black hole morsels, micro black holes the size of asteroids, may form, emitting detectable Hawking radiation that could unlock new physics. This essay explores the concept of black hole morsels, their theoretical foundation, their potential to challenge existing physical paradigms, and the implications for future research. The foundation, Hawking radiation, and its challenges. Hawking's revolutionary idea. Stephen Hawking's 1974 paper, Black Hole Explosions, published in Nature, proposed that black holes emit radiation due to quantum effects near the event horizon, the boundary beyond which no information or matter can escape. This phenomenon arises from virtual particle-antiparticle pairs that form in the vacuum of space. Near a black hole, one particle may fall into the event horizon while the other escapes, effectively reducing the black hole's mass and emitting radiation. This process, dubbed Hawking radiation, implies that black holes can slowly evaporate over time, potentially ending in a final explosive burst. The temperature of Hawking radiation is inversely proportional to the black hole's mass. For stellar mass black holes, approximately 5 to 50 solar masses, this temperature is so low, on the order of microkelvins, that the radiation is practically undetectable against the cosmic microwave background. For example, a black hole with the mass of the Sun would have a Hawking temperature of about 10-8 K, producing radiation far too weak for current instruments to observe. This has made direct confirmation of Hawking radiation a significant challenge in astrophysics. The quantum gravity puzzle. Hawking's theory is significant not only for its implications about black hole evaporation but also for its potential to probe quantum gravity, a theoretical framework that reconciles general relativity with quantum mechanics. General relativity describes gravity on large scales, while quantum mechanics governs the subatomic world. The two theories are incompatible at extreme scales, such as those near a black hole's event horizon. Hawking radiation, which encodes information about the quantum structure of spacetime, could reveal deviations from the standard model of particle physics or hint at phenomena like extra dimensions or supersymmetry. However, the faintness of this radiation from massive black holes has kept these insights out of reach. Black hole morsels, a new window into Hawking radiation. The concept of black hole morsels. The recent study by Giacomo Cacciapia, Stefan Hohenegger, and Francesco Sonnino proposes that during the cataclysmic mergers of astrophysical black holes, smaller micro-black holes, termed black hole morsels, may form. These morsels, with masses comparable to asteroids, approximately 10 superscript 14 to 10 superscript 18 grams, are significantly smaller than their parent black holes. Due to the inverse relationship between a black hole's mass and its Hawking temperature, these morsels are much hotter, potentially reaching temperatures where their Hawking radiation is detectable by current instruments. The formation of black hole morsels is hypothesized to occur during the intense gravitational dynamics of a black hole merger, particularly in the ring-down phase, where nonlinear gravitational effects dominate. These effects could cause small-scale instabilities, pinching off tiny black holes in a process analogous to the formation of droplets during neutron-star mergers. Unlike their larger counterparts, these morsels would evaporate quickly, within milliseconds to years, emitting bursts of high-energy particles, such as gamma rays and neutrinos, in a spherically symmetrical pattern. Detectability, and observational prospects. The key to the Morsel hypothesis lies in its testability. The high-energy gamma rays emitted by evaporating morsels, with energies in the tera-electron-volt (TeV) range, could be detected by atmospheric Cherenkov telescopes like the High-Energy Stereoscopic System HESS, in Namibia, the High-Altitude Water Cherenkov Observatory, HAWC, in Mexico, and the Large High-Altitude Air Shower Observatory, Lhaaso, in China, as well as satellite-based detectors like the Fermi Gamma Ray Space Telescope. These instruments are sensitive to photons in the 100 gigaelectronvolts to 100 TeV range, making them ideal for detecting the distinctive fingerprint of Morsel radiation, which differs from typical gamma-ray bursts due to its isotropic emission and delayed timing relative to gravitational wave signals from the merger. The researchers have used existing data from Hess and Hawc to place upper bounds on the mass of morsels produced during known black hole mergers, marking the first observational constraints on such phenomena. For instance, a morsel with a mass of 10 ⁻15 grams would evaporate in a few hours, producing a burst of gamma rays detectable by these telescopes. The time delay between the gravitational wave signal, detected by observatories like Ligo or Virgo, and the gamma ray burst is correlated with the morsel's mass, providing a unique signature for identification. Implications for physics. Probing quantum gravity. The detection of Hawking radiation from black hole morsels could open a new frontier in physics. Because the radiation encodes information about the quantum structure of spacetime, its spectral properties could reveal deviations from classical general relativity or the Standard Model. For example, unexpected features in the gamma-ray spectrum could indicate the presence of extra dimensions, as predicted by string theory, or new particles associated with supersymmetry. These energy scales are far beyond the reach of particle accelerators like the Large Hadron Collider, making black hole morsels a natural laboratory for probing high-energy physics. Dark matter and early universe physics. An intriguing possibility is that black hole morsels, if formed in the early universe, could contribute to dark matter. Primordial black holes, created during the universe's inflationary period, might have masses similar to those of morsels. If these objects have not yet evaporated, their Hawking radiation could provide clues about the early universe's conditions and the nature of dark matter. The detection of Morsel radiation from astrophysical mergers could thus have cosmological implications, shedding light on the universe's formation and evolution. Challenges and skepticism. Despite the promise of the Morsel hypothesis, challenges remain. The exact mechanism for Morsel formation is not fully understood, as solving Einstein's equations in the complex environment of a black hole merger is computationally intensive. Critics, such as physicist Badri Krishnan, argue that there is no robust theoretical framework for Morsel production, and their existence remains speculative. Additionally, the assumption that all morsels have uniform mass and negligible spin may oversimplify the problem, as real black holes typically rotate. These factors could alter the radiation's spectrum, complicating detection efforts. Future directions. The researchers are optimistic about refining their models and collaborating with observational astronomers to search for Morsel signatures in archived and future datasets. Advances in multi-messenger astrophysics, which combines gravitational wave and electromagnetic observations, could enhance the chances of detection. For example, the Ligo-Virgo Kagra collaboration continues to detect black hole mergers, providing opportunities to correlate gravitational wave signals with gamma-ray bursts. Future telescopes, with improved sensitivity, could further constrain the properties of morsels, potentially confirming or refuting their existence. Numerical simulations, such as those using the Black Hawk code, are also critical for modeling morsel formation and radiation. These simulations could help predict the mass distribution and spin of morsels, addressing current theoretical uncertainties. If morsels are detected, they could not only validate Hawking's prediction but also provide a new method for studying quantum gravity and fundamental particle interactions. Conclusion? The hypothesis of black hole morsels represents a bold and exciting extension of Stephen Hawking's theory of black hole radiation. By proposing that tiny black holes formed during mergers emit detectable Hawking radiation, researchers have opened a new avenue for testing one of the most profound ideas in theoretical physics. The potential detection of these morsels could challenge our understanding of black holes, quantum gravity, and the fundamental laws of the universe. While uncertainties and skepticism remain, the prospect of observing these strange new objects with current technology underscores the dynamic interplay between theory and observation in modern astrophysics. As we continue to explore the cosmos, black hole morsels may illuminate the quantum nature of gravity and reveal the hidden secrets of space-time.